Welcome. We're going to go over some select problems in Chapter 10. Problems including 6, 7, 8, 10, 12, 14, 21, and 29. Starting with problem 6. Calculate the mean ionic activity for 0.035 molal sodium phosphate tribasic solution for which a mean activity coefficient is 0.685. For this first one, we need to calculate the mean ionic activity, given our molality, our salt solution, and our activity coefficient. Well, activity is equal to plus or minus. Mean ionic activity is the mean molality over m naught times activity coefficient. So we need to find out m plus or minus. To do that, m plus or minus is going to equal the product of the cation coefficient to the cation's coefficient power, or the anion coefficient to anion coefficient power, over the total number of ions times molality. So m plus or minus is going to be equal to 3 cubed times 1 to the first all over 1/4. So, and then that's times our molality of 0.0350. Running that. So essentially, m to the 27 raised to the power of 1/4 times 0.0350 gives us a m plus or minus of 0.07978. So our activity is going to be 0.07978 divided by 1 times our activity coefficient of 0.685. You do that, and you'll get the mean ionic activity as 0.05465 as our answer. 546 as our answer. Problem 7. At 25 degrees Celsius, the equilibrium constant for the dissociation of acetic acid, Ka, is 1.75 times 10 to the negative fifth. Using the Debye-Hückel limiting law, calculate the degree of dissociation in a 0.15 molal and 1.50 molal solution with the iterative calculation until the answer is constant within plus or minus 2 in the second decimal place. Compare these values with what you would obtain if the ionic interactions had been ignored. Compare the results with the degree of dissociation of an acid, assuming the activity coefficient, the mean activity coefficient, is 1. So this one is a little bit more involved in that we are trying to find what is the Ka. We have a Ka. What is the dissociation percent using the iterative approach to the Debye-Hückel limiting law? And of course, you gotta remember a Ka is the product of the products over reactants raised to the power of their coefficients, which in this term would be x squared times the activity coefficient squared and the initial concentration minus x. And so in order to actually, you can get close, you can get really close without doing this, without the quadratic, but to be the most exact, you should do the quadratic, which is the negative b plus or minus the square root of b squared minus 4ac all over 2a, where at any given time, B is going to be, A is going to be 1, C is going to be HA times KA divided by what? Gamma plus or minus squared. And I mean, I guess we could leave A as gamma plus or minus squared, but and B being negative what, KA. Wait, no, that'd be C is the negative, and B being KA divided by gamma plus or minus squared. So I already have a lot of this worked out, so we're gonna do this pretty simply. But some of the things we need is I is equal to M over 2 the V plus times Z plus squared and V minus Z minus squared, and we'll need that to calculate the gamma plus or minus. That gamma plus or minus is equal to the exponential of negative 1.173 absolute value of the charge Z plus and Z minus square root of I. So the iterative approach allows us to essentially, we do this multiple times, we get a new gamma plus or minus each time, and we can use that to slowly but surely solve and get the same answer over and over and over again. So, that in mind, the starting with the molality of 0.15. Molality of 0.15 over 2 equals, actually, I'm jumping at the gun. No matter what, I is going to just be whatever x is. We're measuring the ionic constant is going to be just whatever x is divided by 2, 1 times 1 squared plus 1 times 1 squared, or negative 1 squared. So that's going to be 2 over 2. So I is just going to be equal to whatever the concentration of x is. And that means our gamma plus or minus is going to be just equal to exponential of negative 1.173 1 times 1, so square root of x. So, and so, with that in mind, the first thing we do is we solve the quadratic with gamma plus or minus 1 being as 1, and we approach C and define what is our x. That is absolutely our first step. So this is going to be the same answer as if we had done this without any interaction. This first quadratic, I'm not going to show all the work for the quadratic, but the first quadratic, if gamma plus or minus is equal to 1, then we get x is equal to 0.001611, we'll say 4. Because we're only really getting to the second decimal place. See where it really changes. Now, if I didn't include the quadratic, it would be 0.0016202. So not a huge change right off the bat, but we'll see how it changes as we now plug this value into the I. So we plug that into our I, get that, and then plug it into our gamma, and we get, now with this value, that's also equal to the I, we get our first real gamma, plus or minus 0.954. We'll say, we'll take it one more place than it asks us to take it for now. Now plugging that in to our equation with the gamma plus or minus, we can run our values again. So running that again, our new x, which is our new I, so running that through the whole quadratic again, gets us 0.00168, we'll say 9. That's changed a bit. We got to try it again because iterative. We're looking at, okay, that's definitely changed greater than plus or minus 2 in the region. So running that through another time, so how does that change our gamma? Our gamma now is, I can just say, the activity 3 is now 0.95, we'll say 29. It's definitely within plus or minus 2 of in the second decimal place. So let's run this one last time, 0.9529. So this is one of those things where having something like Excel or something like a quick quadratic solver is actually a big help, because that means we don't have to type this into a calculator each and every time. So this third time, our third x is now, our x for the third situation is 0.001691. So now we have within plus or minus 2 in the second decimal place of x. So let's look. Now for the actual thing they asked for is dissociation, the degree of dissociation. So that's going to be x divided by our m of the HA times 100. So without the effects of ions, it is 0.00161. If we divide by 0.15 without the effect, so with gamma plus or minus is equal to 1, we have it's 1.07% dissociation. With the effect, 0.01691 divided by 0.15. With the effect, when gamma plus or minus is 0.9529, the percent dissociation is 1.13. And now we're going to just run this same process over again, except with 1.5 molar. So in this case, quadratic may not actually be necessary, because 1.5 molar is going to put this in the realm of even less of an error. But we can run it either way. So run the same way. So if gamma plus or minus equals 1 at 0.50, so with the quadratic we get something like 0x is equal to 0.00511, we'll say 5115, and without the quadratic you get 1, 2, 3. So, maybe it's enough, maybe it's not enough. We'll see as it goes. So there's our first x. So that's our x sub 1. No, y sub. So running through the same process. How does that change our our gammas at the second iteration, our second run through? Now our gamma has dropped down to 0.9195. That's a little bit more significant. So let's try our next thing. So our x at the second iteration, the second iteration is 0.00556. Well, let's say 62. So that's definitely big enough change. So how does that change our gamma for the third iteration? Now gamma, the third iteration is 0.9162. Run it again. My third iteration of x has now dropped to 0.00558. We'll say 2. Now we're within plus or minus 2. We can stop there. Plus or minus 2, and so we can stop there. You could keep going and maybe it'll get a little bit closer and closer, but all we need is plus or minus 2 in the second decimal place. So let's look. Degree of dissociation, how it has changed. 0.005115 divided by 1.5 times 100 at no interaction, it is 0.341% dissociation versus when gamma is assumed to be 1. When gamma is our 0.9162, 0.005582 divided by 1.5, with the degree of dissociation is 0.372. So not a huge change, honestly, but you're getting more and more accurate each time you go. It's not, as I said, doing this by hand, very, very tedious. Doing this on like a document like Excel, a lot easier. You just have to make sure that Excel doesn't quite understand the circular logic, so you can't have it self-referential. So you have to have a separate thing and then plug the new number in each time. But either way, that is how you do problem 7 with the iterative approach. Problem 10. Calculate the enthalpy of reaction and the Gibbs of reaction for the following reaction. Barium nitrate and aqueous and potassium chloride aqueous goes to form barium chloride solid and potassium nitrate aqueous. Number 8 is surprisingly easy, so long as you keep one thing in mind. Always check the numbers in the back of the book. There's actually a typo in my textbook. It's the stupidest typo ever. We'll get to that in a second. So, the easiest way to do this is you have to split the individual aqueous states into ions. So we have barium 2 plus, 2 NO3 1 minus, 2 K plus, 2 Cl minus as our reactants. BaCl2 solid, that stays together, and 2K plus, and 2 NO3 minus. If you remember your good old-fashioned net ionic equations, you can actually save yourself a lot of time. That 2K plus cancels 2K plus. 2NO3 minus will cancel 2NO3 minus. So all we need is our barium, our chloride, and our barium chloride. So we look up the values in the back of the book. depending on which book you use and which version of the book depends on what numbers you get. The numbers from the current edition has the delta H of my barium 2 plus negative 537.6. My chloride negative 167.2, and my barium chloride negative 856.6. However, the answer key in the back of the book uses a previous edition's uh, delta H of negative 855. Old edition, which, whoops, if you're trying to get your number to match perfectly, that's where you get into a problem. So, delta H is simply, we'll use the current edition, because why would they put the current edition wrong numbers in? Products minus my reactants, negative 537.6 and negative 167.2 times 2. If you were to do this, you would get an enthalpy of 15.4 kilojoules. However, if I'm using 855 instead of 856.6, you would get 17 kilojoules, which is what they give you in the back of the book, which is really frustrating when you're like, how are they doing that and getting different numbers than me? I don't know how. Thankfully, I have more than one edition of the book. And if you use even a different edition, a different textbook with slightly different delta H values, once again, you're going to get a different value. I think I got 13 kilojoules, 13 some odd kilojoules. So, well, yeah, it's just foolish. So delta G, same way, same way. Delta G has this negative 560.8, negative 131.2, and negative 810.3. Now, the other version of the textbook has this as negative 806.7. Don't ask me why. Don't ask me why. But so delta G is just then calculated negative 810.3 minus the reactants negative 131.2 times 2 and the negative 560.8, and that would give your delta G as positive 12.9 kilojoules. And of course, if you do it if you use the 806 instead of 810, you're off by a little bit and you get like 16.3 kilojoules. So very silly, but surprisingly easy. Just you got to look up your aqueous and aqueous ions. Now, we could have added the potassium, we could have added the nitrate, but that just, since they're on both sides, they would just cancel out.
Problem 12. Calculate the Gibbs of solvation in the aqueous solution for rubidium plus aqueous using the Bohr model. The radius for the rubidium ion is 161 picometers.
Number 12 is largely just a careful watching of units. It's the utilization of the following equation to find the Gibbs of solvation with z squared times charge of electron squared times Avogadro's number over 8 pi epsilon naught times r and times the 1 over epsilon sub r minus 1. So so PB, it's RB plus 1. RB plus 1. So the charge is just 1 squared. Electron is 1.6021765565 times 10 to the negative 19th coulombs. that's squared, times Avogadro's number, which is 602214,129 times 10 to the 23rd. It's atoms in a mole all over 8 pi times the permittivity of free space, which is 8.854187817 times 10 to the negative 12 coulombs squared per joule meter, and we're timesing our picometers in 161. So the key thing here is to convert meters into picometers into meters. So 1 meter is 10 to the negative 12 picometers. Once we do that, we multiply our solvent-based E sub r, which is 1 over 88 minus 1. And I'm not going to go through all the math right there. It's already worked out for me. If you work that out, that would give you something like, I went ahead and converted this into kilojoules rather than leave it as joules. Got something like 400, the 1 over 88 minus 1 makes it negative, so negative 427 kilojoules per mole.
Calculate I, mean ionic activity coefficient, the mean activity for a 0.0120 mole solution of sodium phosphate tribasic at 298. Assume complete dissociation.
Number 14 requires us to calculate I, activity coefficient, and mean activity for sodium phosphate given a molality. So the first thing we can calculate is I, which is simply the molality divided by 2 times the coefficient, so 3 times the charge squared, 1 squared, plus the anion, so that'd be coefficient 1, but then negative 3 squared. So 9 plus 3 is 12, divided by 2 makes that 6. So our I is something like 0.072. Our activity coefficient is the exponential of essentially a constant, 1.173 times the absolute value of the charges. So 1 times a negative 3 is just positive 3, square root of our I. I've already calculated that as well. So our activity coefficient is rather low, 0.38897. But now to calculate our activity, we need the average molality for ionic molality, which requires us to take into account our coefficients. So m plus or minus becomes, so 3 cubed times 1 to the first all over 1/4 times our molality, which is, as I said, 0.012. So if I do that, our m plus or minus becomes 0.02735. So our effective molality is a little bit higher than it would be otherwise. So our last step, A plus or minus, just becomes 0.02735 times our 0.38897. And so the activity is only 0.01064. All in all, the effective molality is dropped by just a little bit. But that is number 14.
1021. The base dissociation constant of dimethylamine, there's a typo in here, but dimethylamine plus water goes to dimethyl ammonia and hydroxide, is 5.12 times 10 to the negative fourth. Calculate the extent of hydrolysis for a solution of 0.210 molal solution of dimethylamine in water using iterative calculation until the answer is constant within plus or minus 2 of the second decimal place. Repeat the calculation for a solution that is 0.500 molal in sodium nitrate. You need to use iterative calculation in this case.
For number 21, it's another iterative problem. They want us to consider the base dissociation of dimethylamine. Of course, there's a typo where they changed dimethylamine to monomethylamine in the process of adding that to water. These writers are not perfect. Mistakes are made. H2 plus and OH minus. So just like number 7, except there's a secondary part. So we're going to do quadratic, but basic idea is that first, set up our quadratic and solve for our x. So x squared over base minus x. So first step is solve for x, assuming activity is 1. So assuming activity is 1, the first x you get, x of 1, when y, if we make the assumption y plus or minus is equal to 1, is 1.702 times 10 to the negative second. Now we use that, plug that into our I is equal to m over 2, which m is our x, and 1 to the first plus 1 to the first, that's 2. So I is also equal to x. Now our y plus or minus is, of course, equal to the exponential of negative 1.173 times the absolute value of 1 times 1 times the square root of our I. And we just got our I from there, so our activity coefficient for the that we're going to use for the second iteration is going to be dropped surprisingly to 0.85812. Okay. 85812. Then we're going to use that to calculate our new x. Calculate our new x, run that through again. That through, we get x at 2 to be 1.1741 times 10 to the negative second. And then we run that through, gamma plus or minus 3, we get 0.88065 now. Run it through again, x to the third is 1.144 times 10 to the negative second. It's a little bit off, so we have to run that one more time to get, so gamma plus or minus 4 is 0.88205. And that gets us our x of 4 of 0.0114. We'll say 44. So 1.14 essentially 3.9, which rounds up to 4.4. So at this point, it is not moving anymore. It is done, and that is the concentration. So then, from with that in mind, what's the degree of dissociation? So 1.1439 times 10 to the negative second all over the 0.210 times 100 gives you 5.44% dissociation. 5.44%, 5.44% dissociation. Now, the part B wants you to consider what would happen if you had a big chunk of 0.5 molar sodium. We had 0.5 m sodium nitrate in there. So the big change is when we go to I. So the first gamma plus or minus, where we say it's 1 and x is 1.1741. Well, sorry. Yeah, x is 0.702 times 10 to the negative second. Let's see how this changes our I, because that's going to be important. How do we change our I, and how does it change our gamma? Well, I, remember, is the sum of I is equal to 1/2 times the sum of m plus z plus squared plus m minus z minus squared. So it becomes 1/2 times 0.5 times 1 plus 0.5 times 1 plus x times 1 plus x times 1. So essentially, it becomes 1 plus 2x over 2. And so 1 plus 2x over 2 becomes, let's see, 1. So that becomes 1 plus 1.702 times 10 to the negative second divided by 2. Essentially, so I has now become 0.50851. Plugging that into our gamma, to find our gamma plus or minus 2. And so the exponential e to the negative 1.173 square root of that becomes 50851 0.433, what to say, 2. And let's try our new quadratic. New quadratic says, so on my second iteration, my x sub 2 is now 2.25 times 10 to the negative second. And now let's try one more time, see if we have to iterate this another time. So I now becomes 1 plus 2 times x divided by 2. My I has now gone to, my I has now become 0.52253. And my y plus or minus at the third is 0.4283. Let's see how that changes things. my third iteration, x sub 3 is 2.277. 7, which I'm going to say 2.28, but I don't think it's going to change anymore after that. It's not going to change anymore after that. So with that in mind, we take that and divide that by that 0.21 times 100, and you would get how much would it dissociate at that point? 10.84%. So at greater ionic strength, you end up having actually much larger, with more ions, you have much greater dissociation.
Finally, 1029. Calculate the pH of a buffer solution that is 0.200 molal in acetic acid and 0.15 molal in sodium acetate using Davy's equation to calculate the mean activity coefficient. What pH value would you have calculated had you assumed that activity coefficient is 1?
Okay, for this last one, we're to calculate the pH of a buffer. That's 0.2 molal in HA and 0.15 molal in the A minus, and use the Davy's equation to calculate the activity coefficient. The basic idea is that we need I, and it's just a unique way to use it. So instead of doing the square root of I, it's square root of I over the 1 plus the square root of I minus 0.3 I. So the first thing is to calculate I. I is essentially 0.15 times 1 times 1 squared plus 1 times 1 squared over 2. So I is equal to 0.15. With that in mind, the log base 10 of y plus or minus is equal to negative 0.51 times absolute value of 1 times negative 1. So the square root of 0.15 over 1, 1 plus 0.15 over 1 minus 0.3 times 0.15 over 1. So you have log base 10 of activity plus or minus is equal to negative 0.119429. So I'm going to inverse log. And I get activity coefficient is 0.759, we'll say 57. Now now Ka equals H plus times A minus all over HA times activity coefficient squared. We know this, we know this, we know this. So we're just finding what is H plus. So H plus is going to be Ka times HA over A minus and activity coefficient squared. So 1.5 times 10 to the negative fifth times 0.2 over 0.15 and 0.75957 squared. Let's see. Oh, no, yeah, I did something wrong. I did the wrong Ka, 1.8. So 1.8 times 10 to the negative fifth times 0.2 divided by 0.15 divided by my activity coefficient, 75957 squared. Negative log of that, you get 4.3 4.38. 4.38. And if you compare that to if you had an activity coefficient of 1, how would that change? If your activity coefficient was 1, your pH would be calculated at 4.62. 4.62 if activity coefficient is 1. So honestly, that is a pretty big difference. But I mean, that is how you do that. The Davies equation is really a little bit more complicated, a little bit more depth, but if it avoids the iterative approach at this point, that's not necessarily a bad thing. Okay.